So my name is Mykhailo Vorokhta. I am from Czech University, from Department of Surface and Plasma Science. So today I will share with you a bit some of my experience about near ambient pressure XPS. So I will start the presentation. So I will use laser pointer. Okay. So okay. This is the short outline, so I'm going to start just a bit like in more general way. So I will introduce you what is the in situ and operando methods, because sometimes it is important to understand the difference in all these things, because I think quite frequently I see in literature that people sometimes use these terms in some kind of misleading way. Then, of course, I will start a bit speaking about photoelectron spectroscopy, about just XPS, because as you might understand, the NAP XPS, this is some kind of advanced type of just a normal XPS. And then at the end, I will show you some interesting, or I mean, some examples what can be studied by NAP XPS. So something from my experience, from my work, and something from just from literature. Okay, so let's start. So in situ, ex situ, and operando. So what is the difference? So ex situ, it is something when you take, I mean, we speak mainly about heterogeneous catalysis at this point, because near ambient pressure XPS, it is a technique which is surface sensitive, and usually it is used for study of chemical reactions, of chemical processes which take place on surface of some solid, or I mean, so it might be heterogeneous catalysis when you use gases as reactants, or it can be also liquids. So ex situ means that when you take your sample, you, for example, test it in some reactor. Detect products, and then you take this catalyst after reaction, and you would like to see, I mean, its composition. So then, I mean, it means that you should, bring the sample from air. Yeah. So ex situ always implies air exposure before analysis. In sometimes, of course, you understand that people are trying to exclude this air exposure because it can influence the structure of your sample. So then they, try to measure the samples in situ. So in situ can be in a different context. It can be understood in different ways. So in general, in situ means that you probe the sample at the same environment where, I mean, it has been treated or pre-treated. So it can be like in case of catalysis, you expose it to some gas, to some air pressure, to some gas pressure with pressure, and then at the same environment you can measure it. Or sometimes you can measure it, not directly in presence, for example, gas, but just after it. So you treat the sample and then you measure. And this is, can be used only in case if your changes are not reversible. It means that you treated somehow sample, so you evacuated, for example, the gas, and you measured it with some your method, and then you see the changes. Yeah, so you try to, exclude the air exposure, and you try to catch this influence of your treatment. So also sometimes if you prepare catalyst, it says in some in situ chamber. So it means that you grow the catalyst directly in the chamber. So the treatment is the growing. So for example, it happens if you study some model catalysts when you prepare thin films on the surface of some single crystals, and then you study. So this is in situ. The aim of in situ, as I said, it is to catch the influence of treatment, and and exclude influences connected with sample transfer to the spectrometer. And then operando, this is quite recent like term, which was introduced just like 2002 at one congress, and this means that you do in situ study, so you measure, the influence of some treatment. However, in case of heterogeneous catalysis, you do also detection of products. So you do kinetic measurements. So in this case, you have like some mass spectrometer, for example, which also detects. So you can, be sure that your catalyst is operating. It means that you have some additional advantages, not advantages, evidences that you have production of some products, chemical products, and I mean, of course, you can say that sometimes you can do operando studies even without I mean, doing these kinetic measurements. If you, I mean, somehow tested this catalyst at the same conditions before, and you know that you 100% sure that you have this reaction on the surface. So, I mean, of course, you understand the advantages of in situ or operando studies. It means that on this picture, you can see that, for example, if you prepare some fresh catalyst, and then when you, I mean, before it is active, you need sometimes to do activation. And activation means that you, for example, do, I mean, annealing in presence of hydrogen. It's like reduction, or in presence of oxygen. So you need to treat your catalyst first. It can be done at different temperatures, and then you do a catalytic reaction. And at each stage, at each point, you of course may, I mean, expect to have a bit different surface composition of your sample. So this is nanoparticle, for example. And of course, if you measure sample just before, I mean, the catalytic test, and after, you would have some information. After, it can have a bit different composition, but you cannot be sure what was the composition of your catalyst when you, exposing it to different gases, for example. So this is the advantage. I mean, so when you are able to measure the composition of the catalyst in presence of gas, I mean, you can catch all these structures. So, of course, I mean, there are many methods. I mean, almost all recently, well-known methods which were used usually as a UHV or something, they are developed recently to be able to do this in situ measurements. So you see here some list of them, but of course there are even more. I just show you some with which I somehow familiar. So all of these methods, they have some, I mean, some advantages or disadvantages. They give you different informations, and as I said, among these methods, there is in situ NAP-XPS. So you see sometimes people use NAP-XPS, and NAP-XPS it already means that it is in situ, but somehow they even put here in situ just so it is kind of overload. I mean, is this in situ term. And then you see that for example, infrared spectroscopy, it gives you information about some adsorbed species, about the vibrations of these species on the surface. In NAP-XPS, it is also kind of surface method. XPS by itself, so it's, but however, it is a bit more like probing a bit deeper, and gives you information not only about surface species, but also about atoms at the surface, about the catalyst. Of course, at some points, you might be not able to study some samples by NAP-XPS. In this case, you can use like X-ray absorption or XRD and SACs and so on. All these methods might be used as in situ. Also, neutron scattering and diffraction. Of course, I'm not familiar with this topic, but you, I think, had enough information now from this summer school about these methods. Okay, so also what is popular, or I would say what is usually done, it is when people try to combine many in situ methods when they study, for example, catalysts. So you see on this picture, so sometimes it is not enough to use, for example, only in situ NAP-XPS when you would like to have a complete information about processes which happens with the catalyst, about some intermediate species which appear on the surface. So in this case, you might use many methods. You can have also, as I said, this mass spectrometry or some yes, just to detect the products, and then you can say that you this operando, in situ operando. So people use these words quite in different way, and sometimes they then don't much resolve what the difference between these two terms. Okay, so so as I said, of course, most of in situ methods, they are somehow based on some like X-rays or I mean probing or so on, because you can imagine that if you expose the sample with a gas or liquid, you need that your beam should penetrate this gas to reach the sample. Also, you should have I mean the signal which is I mean emitted by this by sample. It should also be able to penetrate the environment which you use I mean for exposure. And then, of course, in many cases, it is X-rays beams, and of course, a lot of such in situ methods, they are based on synchrotrons. So, but this is just to know. Okay, so let's now go to photoelectron spectroscopy. So, I mean, XPS, it is kind of, I mean, surface method, surface sensitive method, which is, I mean, used usually when you need to do chemical analysis of your surface. So it means that, I mean, if you want to know which, I mean, what elements you have on the surface, what, I mean, chemical state of these atoms, I mean, if it's oxide or metal and so on, so you usually might use the photoelectron spectroscopy. So the method is based on photoelectric effect, which was firstly explained by this guy. This is, of course, I think all of you know this.
No, čau. Ale já už jsem to našel.
For this, I mean, he got the Nobel Prize in 1905. Also, I mean, as a method, it was firstly developed and used in the present way by Kai Zygmunt, who received a Nobel Prize in 1985 for I think developing the photoelectron spectroscopy. Also in literature, you can find some other like abbreviation or other names of this method. It can be ESCA, it's electron spectroscopy for chemical analysis. Also, depending on the energy of photons, which are usually used when you, I mean, do the XPS. It can be also divided on many like sub methods, which are like UPS, it's ultraviolet photoelectron spectroscopy. So it means you use only ultraviolet for, I mean, excitation of electrons, or it can be also called just photoemission spectroscopy. So all this is XPS. And okay, so basics of XPS is quite simple. So as I said, it is based on photoelectric effect. I mean, it means that you have some source of photons. Usually it's, as I said, X-ray or in ultraviolet region. And then, I mean, you irradiate the sample, you ionize atoms at the surface, and you collect the electrons which are emitted from the surface. And then, I mean, by knowing the kinetic energy of the detected electrons, so you can easily calculate the binding energy of these electrons. It means that, so, and you understand that binding energy, it is, I mean, for each element, usually they have its own electronic structure, so you can, I mean, using some tables, some references, easily answer what elements you have there. If you, I mean, when you measure some peaks. Yeah, so I mean, yeah, it's here like to explain. So when you have an atom, usually when you do XPS, you detect, I mean, you are interested more in some core level spectra. So it means core level electrons. However, I mean, of course, you can do UPS, which means that you can also detect the valence band electrons. Because usually if you use X-ray photons with high photon energy, I mean photons with high energy, I mean usually the valence band is quite, I mean to excite electrons from valence bands, it's like a bit low probable, there is a low probability, low cross section for this process. So I mean mostly it is inertial. Okay, and what is also important that in photoelectron spectroscopy, you are interested in electrons which are come directly from atoms to the analyzer, to the detector, yeah, because as soon as it means without any scattering or with completely elastic scattering, it means that as soon as there is some inelastic scattering and the electron is losing a bit of energy, then of course you already cannot be sure what was the initial binding energy of this, because So it means that all these electrons would create the background, so it is some kind of secondary electron. And yeah, so just to as I said, the XPS, it is method which is can be used for like qualitative analysis. So you can measure some like electronic structure of atom by it. So when you, for example, I mean, analyze the all emitted electrons from some surface, you can have a photoelectron spectrum, which is shown here. There you will have different peaks, which are somehow correspond to electronic levels inside the atoms. So, for example, this is the spectrum of ruthenium metallic foil, and you see that here you see only peaks which are related to ruthenium, of course. But if you would have there some like oxygen or some other elements present on the surface, you would see some other peaks. Yeah. So first you measure usually the survey or the wide scan, which I mean tells you just I mean quickly what elements you have there, and then of course you are interested in some special regions which you measure in detail. So in this case you can measure the most intensive peak of ruthenium 3D, and then I mean also by measuring its energy, you can be sure that this is like ruthenium, yeah, or whatever. So each chemical element has its own electronic structure. So by measuring peaks, measured peaks, they are, I mean, it's like footprint for an element, yeah. So sometimes, of course, happens that some peaks of different elements they overlap. So in that case, you need to measure like several different core levels, because it is very rare that several core levels would overlap. So usually, I mean, one can overlap, but I mean that more peaks are overlapping, it is not the case. So also, if I mean just by knowing what type of element, it is not all information which you get. Also, you can have information which tells you something about chemical like environment of atom at the surface. So if there is a chemical bonding between atoms with some neighbors, usually it means that the valence electron of an atom, they would a bit somehow share with other atoms with surroundings. Yeah, so you have bond formation in case of, for example, carbon with fluor. When it interact, you can expect that there will be like a very like polar bond. So it means the fluor is very electronegative, and it would pull a bit valent electrons for carbon. And this process results in also in change of I mean levels inside the atom. So all core electrons, they would feel this process, this like restructuring of valent orbital, and then you can I mean do like a bit fine analysis of this, I mean of the elements. So it means, for example, here you have on the surface quite complex molecule which contains several different carbon atoms for different carbon atoms, which are surrounded by different I mean environments, yeah, by different other elements. And in all cases, I mean, you see that you have different peaks, which actually, I mean, corresponds. I mean, all these peaks corresponds to the type of carbon inside the molecule. So this means that you can do like a kind of I mean, to find the oxidation state of an element with XPS. So also, I mean, beside the qualitative analysis, I mean, the detection of type of elements and its chemical state and so on, you can also do a kind of quantitative analysis. So you can try to get some information about concentration of atoms at the surface. So for this, I mean, you should understand that the peak intensity or photoelectron peak contains many different contributions, which comes from also from material property, flux of your X-ray source. So it means if you use a higher intensive source, it means that you would have, I mean, a proportionally higher peak intensity. Also, there is parameters for analyzers. Like most important is maybe transmission function, which means that some amount of signal is usually lost at the analyzer. So it means not you detect 100% of electrons which enter the analyzer. So there is, I mean, some dependence with energy. So, and also you can have different optics, which would change the area of analysis on the surface, so on. It means what I want just to say that all these parameters, I mean, related to analyzer and X-ray source can be calibrated for one spectrometer. Yeah. So in that case, I mean, if you take some materials and you also calibrate the cross section, I mean, the photoionization cross section, like probability for photoionization, and you know what is the lambda, and this is the parameter which tells you from which depths the electron can come to the surface from sample. So all these things can be somehow, I mean, measured using some calibration samples, and then it means that you can use the only one parameter, which is called sensitivity factor. And then, I mean, the intensity of a peak for one element, for some element, will be just proportional to concentration of atoms of this element at the surface, and it is normalized to this sensitivity factor. So it means that if you measure some unknown sample with the same type of elements, you know sensitivity factor, and you know the intensity of the peak, you can try to calculate some concentration. So do some quantitative analysis. This is, I mean, of course, true only for homogeneous samples. If you have some complex like layer structure and so on, this doesn't work. Okay, and yeah, and this, as I said before, the lambda is important parameters. This is the mean free path of electron inside the material. This path is dependent very much on energy of electron. So I mean, and it is also important to know this parameter, because usually the signal is coming to the surface from depths which is like equal to 3 lambda. So here is the probability for photoelectron to reach the surface. So it means you understand. So if you ionize the atom, I mean the atom somewhere here, then a photoelectron should pass all this layer which is above the atom, yeah, if it wants to reach the surface. And there is, of course, a very big probability that it will be scattered, and then it becomes just, as I said, as a background, yeah. So here is the probability which shows you what is the probability of electron to reach the surface. And you see that from depths which is higher than 3 lambda, there is very, very small probability for electron already to enter analyzer, yeah. So and of course also you should understand that lambda, as I said, depends on kinetic energy of photoelectron, yeah. And this kinetic energy of photoelectron, of course, is related to the energy of photons which you use when you do XPS. So if you use photons which are just some like 100 eV higher in energy than the like binding energy of some photoelectron inside the atom, you would have electrons which have the energy like this 100 electron volt, yeah. So if you use higher energetic photon, of course, you increase the kinetic energy of emitting electrons, yeah, and then you increase the lambda, and then you increase, of course, the probing depth of your material. So why I'm showing this? Because in case of NAP XPS, it is, I mean, very important to analyze only the topmost surface layers, yeah. So, for example, if you have some chemisorphed layer of molecules on the surface, usually it is not higher than one monolayer, yeah. If there are more monolayers, it's usually like some kind of condensation or physisorption, and it not happen at higher temperature. And then it means that for photoelectron spectroscopy in presence of gases, it is quite sensitive, I mean, parameter, I mean, the photon energy. And usually, I mean, the best would be have to work with photoelectrons which are like, in the region of the more surface sensitivity. Yeah, so it means that from 10 or to 100 or so on. Okay. So yeah, also of course you can not only change the if you want to change the probing depth, just the energy of photons, you can also change a bit the angle of detection of photoelectrons. So you understand that if you excite photoelectron somewhere here, it can go for at different directions, and of course if it goes in this direction, it has to pass a bit longer way in order to reach the surface, and the probability to be scattered is proportional to this distance which it should go. So it means that the angle is also parameter which can help you to change the surface sensitivity. So usually people change or photon energy or angle if they want to change the probing depth with XPS. Okay, so I guess now we can go we can move to NAP-XPS. So as I said, just XPS, standard conventional XPS in UHV, it means that you irradiate the surface with photons, you ionize the atoms at the surface, and you try to collect the electrons. Yeah. So by analyzer, so there is analyzer nozzle, some aperture which collect the electron. Yeah, in case of NAP-XPS process is the same. However, you only the additional things which you have, it is the presence of gas. Yeah, so in this case, you can also expect that first you would also have some signal which comes from the gas, because you see that when beam is approaching the surface, it is should penetrate also the environment. Yeah, it should penetrate the gas which is above the sample. So and of course there can be ionization of this gas. So you would have also some electrons which are formed in the gas, and then these electrons can also enter the analyzer. So you would have such so-called signal from gas phase. Yeah, it is one thing. Another thing that yeah. Another thing that the gas would also, of course, enters the analyzer, and this is the problem, as I show next. Yeah, so advantages of NAP-XPS mean that you can analyze this. You can do analysis of a surface. Which is interacting with a gas or with liquid. It's also possible, and then you can try to answer the question: what is the chemical state of atoms at the surface when these atoms are interacting with gas? Also, you can try to answer the question: what adsorbed species you have on the surface? Intermediate reaction, some species. Yeah. And then it means that you can do this analysis of catalytic processes on the surface. Also, you can do other type of studies. You can follow how the surface is oxidizing, for example, or corrosion, because and you do this online. It means that you can follow the dynamics of this process on the surface. Also, sometimes you can study, the samples which have the high vapor pressure. So if it is a case of some biosamples, if you have something that contains water inside, it is very difficult to analyze such samples using UHV XPS, because you need to have, as I said, like low pressure, high vacuum for be able to operate X-ray source and electron analyzer. And in this case, in case of NAP-XPS, you don't have this problem. The high vapor pressure is not a problem, and so on. In some cases, you can also analyze the processes which take on surface of gas sensors. It's also possible. This is somehow related to catalytic processes and so on. And as I said, there are some technical problems in case of NAP-XPS. First is that the beam, as I said, has to penetrate gas, and in different cases it can have different problems. For example, if you would like to have, as I said, very low photon energies, just some 100 eV higher than the binding energy of electron inside. So then you have electrons with low kinetic energy, so you are in this most surface sensitive mode. The problem is that then you can have very big absorption of the beam by gas, and also you can have the absorption of of the electrons which are leaving the surface, because as I said before entering the analyzer, the electrons should penetrate this environment which is above the sample. And if kinetic energy of photoelectron is low, it means that the scattering is much much more probable. So I will show this all on my next slides. And another technical problems is that you, of course, as I said, have entering of the gas to analyzer, and also if you use some X-ray source, this gas can also enter the X-ray source, and the operation of X-ray source and the analyzer requires high voltage, and then gas is of course not good for those things, and it means that you need somehow to try to exclude the influence of gas on analyzer and X-ray source. So just before we go to NAP XPS, instrumentation, I just would like to remind you, just standard UHV XPS looks somehow like it's shown here. You have some UHV chamber, ultra high vacuum chamber with low pressure inside. You put sample, there is a X-ray source. It can be also just a tube coming from synchrotron. That irradiates your sample. Then you have electron analyzer. Or as I said, all these and these parts, they should be in high vacuum, because the detector, it usually requires like a voltage which is higher than I think 12 kilovolts, and because this is kind of multi-channel plate and X-ray source. Yeah. So in this case, if you have some gas inside here or here, it would not work, because you would have just simply shorting. Yeah. And okay, and have to try to build the NAP XPS. The first way how it's possible is try to somehow isolate the X-ray source and the detector from the gas. So in case of X-ray source, it is relatively easy, because of course it depends on the energy for your X-ray source. However, if you have some conventional X-ray source like aluminum K-alpha, which produces photons with energy like about 1.5 kilo electron volts. In this case, you can simply just use some membrane, which is relatively almost 100% transparent for the photons, and it's quite strong enough to keep the pressure which you have. So you have the analysis chamber, which is filled with the gas, and you have the X-ray source, which is isolated from the analysis chamber by using this membrane. It has its own like evacuation system, differential pumping. The same can be tried to do for analyzer. So it means that you also can try to put here some membrane which would protect the analyzer from high pressure of gas. However, as you understand, I told you that usually if you have some solid, the mean free path, so the path of electron inside the solid before scattering, is usually some nanometers. So it means if you want to have penetration of electrons through such membrane, you need to have it seen as maybe 10 nanometers or even low. And of course, such a thin membrane usually very, very weak. It is very difficult, to have it stable, to protect it from high pressure. You cannot increase pressure too much. You can go for, relatively to low pressures. And as I said, it is dangerous because it can break at any moment. Yeah. So in this case, people try to use a bit more safe construction, when you have not the membrane, but you have a small aperture here, which with which you approach the surface to closer distance, so you can collect the electrons from the surface. and you don't have there any membrane. You have only several like pumps, like you have differential pumping of analyzer. So it means that analyzer, the detector should be a bit farther from the analysis chamber, because you need some distance to decrease the pressure. And in this case, I mean it is much more safety. And okay. What is also important that in some cases, I mean, it is not very practical to fill the chamber completely with gas or vapors, you know, because as soon as you fill it, I mean, without bake out, I mean, you would have relatively poor pressure inside such a cell, yeah, or in such a chamber. Even I mean, it is quite difficult to evacuate such cells and so on. So in this case, people prefer to use another design, which is called chamber-in-chamber design, when you have a small chamber inside a normal standard UHV chamber. And when you need to do like a near ambient pressure study, you simply approach with the sample, with the cell to analyzer, you dock this cell to the analyzer, and then you do NAP XPS. Of course, if you don't need to do, or you want to prepare in situ some catalyst, and you need for this kind of UHV, so then you simply retract this cell to another chamber, close the valve, and then here you can have 10 in minus 10 millibars pressure, yeah? And you can do also for not only NAP XPS studies, but some UHV studies. And all these chambers are called backfilling chamber NAP XPS, and this is the chamber-in-chamber. So of course, as I said, in case of NAP XPS, the analyzer, it is a bit farther from the sample, because I mean, you have several pumps here, and in this case, you can imagine that I mean, if you just simply have some apertures, I mean, which are I mean, for collecting the sample, so the electrons, you would lose a lot of signal, because I mean, there is a decrease of the signal as the distance from the source is increasing, as you know, as 1 divided by the distance, yeah. So this is quadratic law. And then it means that in this case, usually people use some special electrostatic lenses, which try to keep the electrons as one beam, and I mean to transmit them to analyzer, yeah. So it is very important parameter. Yeah. So here, this is the I mean, how normally such analyzer look like. This is the spec snap electron analyzer with differential pumping, the same we have in our laboratory. So you see that here you have, as I said, several pumps. Even an analyzer, it has its own pumps. You have many, like some gauges which are carefully follow the pressure inside. So I mean, the analyzer would not start until the pressure in the last stage would go lower than in -7. So inside the analyzer looks, I mean, quite, I think, expectable. As I said, there are some lenses which are electrostatic lenses, which have some potential to keep the electrons, I mean, as a one beam. So then you don't lose much. At the end of this analyzer, you have this small nozzle, this small aperture with size like 700 micrometers. Standard size is 300 micrometers, because if you use the nozzle with like kind of higher size, I mean, you would have already too much gas entering the analyzer, so those pumps cannot, I mean, decrease the pressure lower than 10 in -7, for example. Yeah. So here is some calculations which shows you that when you, of course, I mean, I told you before, maybe on this, I forgot to tell you that it is the best is that if you approach with the nozzle as closest as possible to the sample, because I mean, as soon as the distance of the nozzle is increasing from the point of irradiation, I mean, when the X-ray, so when the X-ray beam comes, you lose the intensity, yeah. And then I mean, as soon as you approach the surface more and more, you take more electrons from the surface. So this is the things. However, I mean, another thing is that when you approach with the nozzle too close to the sample, you create kind of like low pressure above the sample, because I mean, here you have like vacuum, yeah, or like low pressure, because there is a pump which decreases the pressure to much lower than this pressure inside the cell. So it means that here is some calculations which shows you what would be the pressure at different distances from the nozzle, yeah. And you see that as soon as the distance is lower than 1 diameter, so the one like size of the aperture, you would have the local pressure above the sample a bit lower than I mean just the field pressure in the cell, yeah. So it means that you cannot approach closer than 1 diameter. So usually it is the standard distance at which you measure. I mean, so it means that you should approach with the nozzle, which has size like 300 micrometers, to the distance which is also 300 micrometers from the surface. If you don't want to, I mean, to say that I mean you have a bit lower pressure above your sample, above your surface, than you expect. So here is some calculations which shows you, I mean, how many pumping stages you usually need depending on the pressure. So it is like the case when you have here some pump which pumps, then there is an aperture. I mean, this is quite simple calculation, and it shows that if you use standard turbomolecular pump and you have the nozzle with size like with radius like 150 micrometers, you would have the decrease of pressure like by 5 orders. Yeah, so it means if you use 1 millibar here in the first pumping stage, you should have like 10 in minus 5 millibar. So it also tells you that you need more than one pumping stage, because 10 in minus 5 is usually not enough for analyzer to work. Yeah, so as I said, the one problem which you have with NAP XPS could be signal attenuation by gases. So you, as I said, you irradiate the surface by X-rays, then these electrons are entering the nozzle of, I mean, this entrance aperture of analyzer. However, they should pass some distance from the surface to the analyzer, and usually, I mean, it results in some scattering of electrons on the gas. Yeah, so depending on the pressure of the gas, you will have different, I mean, probability for the scattering. Here is some calculations. You understand that you simply use the Beer-Lambert law for absorption of electrons which are coming through some like environment, yeah. And then I mean it is important that the mean free path, and this is the kind of probability value which shows you the probability for scattering is I mean depends on the pressure as 1 divided by P, yeah. So as higher pressure, lower lambda, it means the more signal will be, I mean, this signal which you normally could measure in vacuum without gas. As soon as you fill the environment by the gas, you would, I mean, have a bit lower signal, which I mean, at the analyzer. Yeah. So here are some experimental like measurements which shows you how this lambda depends on the energy if you use like 1 millibar of different molecules. So it also means that not only pressure but also other parameters like sigma, like sigma, and this sigma, this is the probability for scattering, which depends on the size of a molecule. So smaller molecules like hydrogen, then they I mean scatter less electrons. The bit higher like size molecules, they scatter more, yeah. And you see that in some cases, like in case of this molecule with chlorine, yeah, it is like quite, I mean quite I mean the probability to be scattered is quite high, yeah. And this here I did some calculations with a standard gas, which can quite often used in NAP XPS. It is in case of oxygen. So if you fill with 1 millibar of oxygen and you have the aperture with this 300 micrometer size, then this lambda will be close to 4 millimeters, the mean free pass of electron inside 1 millibar of gas. So then you lose only 25%. However, as soon as you increase the pressure to 4 millibars of oxygen, you would get already only 30% of original signal. So original signal, it is the signal which you would have if there is no gas. So you see that it is quite critical. So you cannot go with pressure very high because you would have a relatively low signal. And for example, I will show you that our nacelle can be filled up to 20 or even 30 millibars with gas, but of course, I mean, then you lose a lot of signal. And normally people work with, I mean, with pressures which are just some 1, 2, 3 millibars. Yeah, here is again some example how different energetic electrons are. I mean, are attenuated by water pressure. So this is torus. I mean, it's close to millibars, the same almost. And you see that depending on energy, you have, I mean, different attenuation. For example, if your electrons, it means that if you use photons with energy, which would result in, I mean, electrons with, for example, 700 eV. So this is the case of just XPS with aluminum alpha X-ray source. You have, I mean, relatively not big attenuation. However, I mean, you see that 1, 2 millibars or torus of pressure would decrease the signal several times. Yeah. However, as soon as you would try to use some UV, ultraviolet, I mean, source or whatever, when you have much lower, I mean, like soft X-ray, yeah, at synchrotron. So, for example, electrons with energy kinetic energy 100 eV, they are attenuated quite strongly. As soon as you see that when you go from 1 torr to 2 torrs, you lose like signal 10 times. Yeah, so from 0 to yeah, from 1. Yeah, so this is when there is no gas, so it's taken as a reference level, and then it's 100 times lower signal. Yeah, just 2 torr of water inside the chamber. So it is very critical in this case. So I mean, also what is important to remember that at some points, as I said, I mean, the beam is penetrating the gas before I mean reaching the sample. Yeah, the X-ray beam. I mean, and then. It means that at some energies, for example, if you have oxygen inside, and as soon as the energy of the beam is approaching the energy of electron inside this oxygen molecule, then there could be absorption line. Yeah, so then you should also count for this. That I mean, at some points, I mean, you can lose some amount of photons which are, I mean, absorbed by the gas. So it is also another parameter. Okay, so the standard sources which are used in NAP-XPS, this is, as I said, can be synchrotron light. It is the most convenient, I mean, source, because you can tune the energy, you can, I mean, change the probing depths, and in case of study some chemical processes and some species on the surface, I mean, usually you need soft X-ray. However, of course, you can also work in laboratory. So there are laboratory NAP-XPSs, and which one we have in our lab. So then you use just a standard X-ray source, which is, for example, aluminum alpha. It should be, I mean, with a high intensity, as high as possible, because you have to focus the beam to small size. I mean, as you have this nozzle with size like 700 hundreds of microns, it means that you should focus the beam also to some size which is a bit higher than this area from which the nozzle is collecting the signal. And then, of course, it can be also in laboratory, you can use some UV lamps. So it's, as I said, usually, I mean, the X-ray source has its own, might have its own some differential pumping. And here it can have the small aperture, which is, as I said, protect the X-ray source from entering of gas. Yeah, so this is usually silicon nitride windows, which are quite transparent for photons with energy, with high energy. Yeah, like in case of aluminum alpha, it is about 1.5 kilo electron volts. And here you see that almost 100% of photons can penetrate such membrane. Of course, as soon as you go to lower photon energies, so I mean, if you use some synchrotron light or some ultraviolet lamp, then you should also count for some possible absorption by this window. Sometimes these windows are coated by aluminum because I mean they are quite weak, they can break quite easily. So if you coat the window by aluminum, you see that aluminum has its own some absorption bands, and they are quite copying the absorption curve for silicon nitride. However, I mean there's also some small differences. And this is the standard UV lamp, which we also have in our lab. This is, I mean, again, it has its own some differential pumping, a small capillary which forms the beam with size of below 1 millimeters. So you can have the photons with energy like 20 or 40 eV. So it is mainly for study of study of valence band electrons. So it means that you can excite only electrons from valence band using such energies. Okay, so as I said, together with NAP-XPS, I mean, with the study of surfaces in presence of gases, you can also do some study with liquids, you know, so you can study the interaction of solid with liquid. So for this, you can use two approaches. One is shown here. This is the use of liquid microjet. So it means you disperse, for example, some solid particles in a liquid, and then you use a microjet, which is, I mean, you have the jet of this liquid, of this suspension, and then you can try to approach with the nozzle to such jet, microjet, and try to analyze it and to analyze the particles inside. Of course, you have a kind of dynamic system, so it means that the particles are continuously moving in the jet. I mean, this configuration is good because of this direction of liquid movement, yeah, inside the chamber. Results that you have only relatively low pressure of vapor pressure around the jet, yeah. So it's 10⁻⁴. Another way that you can directly, I mean, analyze the surface which is being in contact with liquid. However, I mean, of course, you cannot measure with the nozzle inside the liquid. So usually it is done in a way that you dip the sample to the liquid and then pull it a bit, and then you can analyze. I mean, you irradiate this sample. Of course, I mean, you should understand that liquid usually creates a layer which has thickness 700 nanometers on the surface. And usually electrons with energy like lower than several kilo electron volts, they cannot penetrate such a liquid layer. So all those kind of experiments usually done with at synchrotrons when it is used the hard X-ray. Yeah, so you should have photons with energy several kilo electron volts, and then you can do such analysis. I will show one example at the end of such studies. I mean, usually it is done when people try to do some electrochemistry. So they usually have electrolyte and they want to study some electrochemical processes on the surface of some working electrodes. So then they try to use these. Another way, instead of using this dip and pull, you can simply use some rotational disc. So it is rotating. It's I mean, immersing the liquid, and then it's like wet, so you can do analysis of such wet surface. Okay, so this is the standard like how this laboratory NAP-XPS spectrometer looks. So this is the one which we have in our lab. So you have there, you can have many chambers there. The most important for NAP-XPS, this is this analysis chamber, and here is the manipulator with the NAP cell. So as I said, I mean, you can retract the cell if you want to do some UHV measurements, or if you want to do NAP-XPS measurements, you simply approach with this with the NAP cell to analysis chamber and dock the cell to analyzer. So if you look closer, it looks like here. So this is the entrance of the analyzer, and this is the NAP cell. It has the door, so it means that you I mean, can open the door, insert your sample inside, and then you close the door. The door is sealing well, so it means that you can fill this cell with gas inside, and outside you have UHV. Yeah. So if you look on this manipulator and the nap cell, I mean, a bit more closer. I mean, if you want to know what is inside, so there is a, I mean, stage on which you put your sample. So this stage can move. I mean, close and far if you need, and you put your sample here, and then you approach with the stage to the nozzle. Yeah. So this is the nozzle of analyzer, and then all this volume around is filled with a gas. Yeah. And you can heat also the sample simply heating this stage from behind by bombarding it by electrons. Also, there are some other ways of heating. There you can use some special plates which are heated by resistance and current flowing through it. In our case, it is simply bombarding the rear side of the stage with electrons. And here inside, I mean, the stage you have simply vacuum. It is connected with the outside UHV chamber. So the sample can be heated up to 500 degrees C, and you can fill the cell with like maximum 20 millibar of gas. Yeah. So this is, I mean, enough for doing some catalytic reactions inside on the surface of your sample. Of course, as I said, I mean, 20 millibars, it is, I would say, more commercial way of presenting NAP XPS. Usually laboratory XPS works at 1-2 millibars, because higher pressure of gas results already in quite, I mean, low signal and some other problems. Okay, so yeah, what is also important that when you approach with the sample to the nozzle, I mean, it is very difficult to control this approach. I mean, there is no any protection system, so usually you just look inside the camera, inside the cell, you look on the sample, and then you just, I mean, follow the nozzle and its shadow. So then you approach. So it is the standard way how people usually work. Okay, so now I think we can move to the last part of the presentation. This is what can be studied by NAP XPS. So I will show you several like interesting, again, in my opinion, examples. Some are from my like experience, some are from literature. So first, as I said, this is a study of simple chemical reactions on surface of catalyst. So one example, this is study of methane to methanol direct conversion. Yeah, so you know that we have a lot of methane on the earth, and I mean, what you can do with this methane, you can form, for example, simply burn it, or you can try to convert it to methanol, which is already liquid. It is much easier for transportation. It is also, I mean, can be like a starting point for some chemical industry. I mean, you can create more complex chemicals from methanol. And if you want to convert the methane to methanol, I mean, you should pass through the methane oxidation reaction. So there is, I mean, two possibilities. So first one, that if you mix with methane with oxygen, it can completely kind of I mean, dehydrogenate, and you have then the just formation of CO and hydrogen. Yeah, so you like cleave or bonds with hydrogen, and then this carbon is interacting with oxygen, and you. So of course, this is, I mean, not like the way which we want. If you want to convert just methanol to methane to methanol, so you want just to remove one hydrogen from this methane, then I mean, move this hydrogen to oxygen, make some OH, and then this OH interacts with CH3, and you form the methane directly. Yeah, so this is the reaction which we want to have. And usually for such a reaction, people use catalysts. There are like nickel, copper, cobalt, some transition metals. Yeah, and then I mean, it was also shown that in case of presence of some kind of active supports like cerium oxide, you can have some beneficial impact on the catalytic ability of this metal. So in this case, we studied, I mean, some kind of model catalyst. It means because as I said, with XPS, you can study different samples, but of course, if you do study on some powder samples and so on, you usually have problems with surface charging. So powders, they are not connected very well, and when you irradiate them by X-rays and extract electrons from the surface, such powders can easily charge. Then you have some distortion in your spectrum and so on. So it is much better to work with some kind of like in this case very thin layer of oxide on the conductive single crystal. So this is called model catalysts, and they are kind of modeling the situation in real catalysts. So such catalysts usually prepared in the UHV chambers. So you simply evaporate, for example, cerium in presence of oxygen, then deposit some metal clusters on top. So this is some STM images showing how such catalyst looks like, and then such samples, they are quite good for study by XPS because they are not charged, and you can you don't have many problems with it. So okay, so such catalyst was tested. For this methane conversion to methanol, you see that what was first found that if there is just a mixture of methane with oxygen at high temperature, you have completely domination of this reaction. Yeah, so completely like oxidation of methane to CO and CO2 and hydrogen. Yeah. However, it was also found that if you add a bit of water to such mixture, yeah, 1 torr or even more, you can, tune a bit the selectivity of the reaction for formation of methanol. Yeah. So it was, shown by some of my colleagues, and then it was interesting to find why this happens. Yeah, because what is the reaction mechanism which actually some kind of improves or increase the selectivity towards methanol formation. Yeah. So in this case, we prepared several different samples. It was some cerium oxide layers with different coverage of nickel on the surface. It was found that there is also some optimal size of nickel particles on the surface when you have coverage close to 0.15 monolayers. And in this case, the production is the highest. So because there was some interaction, like kind of metal support interaction of these particles with the support. However, this is not very important. What is important that what you can see if you try to apply XPS for such studies. So first you see here the spectra which were measured. So the samples which contained no nickel, pure cerium oxide was firstly exposed to just pure methane, and you see that, for example, if there is no nickel, nothing happened with the surface. However, if there was nickel, the nickel work as a catalyst. It cleaves the bonds between C and H in the methane molecule. So you have formation of two peaks which are corresponding to CHX, which is a kind of methane which lost some number of hydrogens. And then there is some also peak which is COX. So it means that if you have nickel on the cerium oxide, you can have completely the hydrogenation of this methane, and you have formation of carbons which interact with the oxygen on the surface of ceria. Yeah, so you have these carbonyl groups here. However, what was found that if you first pre-adsorb on the surface water, this pathway, which corresponds to the formation of COX, was completely attenuated, and you have formation only of this CHX, species. So it means that water adsorbs on the some, catalytic sites, and it kind of blocks complete the hydrogenation of methane. Also, we did, several studies with, presence of not only methane, but methane plus oxygen. So it means we simulate the reaction, and we try to measure the state of chemical state of ceria and nickel particles. And it was found that as soon as there is increasing water pressure, in the presence. I mean, so we were also adding then the water to such mixture. You see that there is a formation of some nickel hydroxide, and it was kind of, I mean, and there was kind of explanation which told us that if there is a water is interacting with some nickel atoms which are, I mean, it kind of blocks the sites which are active for complete the hydrogenation of methane. Yeah, so and it is why it increases the selectivity to formation of CHX groups, which are then interact with these OH groups and form the methanol. Yeah, so it was so. So what I want to say that I mean, using such studies, you can try to explain the reaction mechanism on some complex surfaces, catalytic surface. Another example, it is I mean, the study of gas sensors. So this was also quite interesting topic, because I mean there is some standard I mean kind of explanation how the gas sensors with metal oxide sensing layers works. So normally it is assumed that there is, for example, some material like tin oxide. It is the very popular metal oxide which used this as a sensitive layer for gas sensors. And then when there is, I mean, the presence of some environment like air which contains oxygen, so the oxygen can chemisorb on the surface of this oxide. So at high temperature, it happens mainly at high temperature. So higher than 200 degrees C, you can have different species on the surface. First, it can be just simply molecule of hydrogen adsorbed, which pulls one electron from the surface. If you increase temperature, this oxygen can dissociate onto atomic oxygen, and they take electrons from the surface. And this is, important because it creates at the surfaces some regions which are contain kind of less electrons, because you understand that SnO2, it is kind of semiconductor which is n-type. So the charge carriers inside are electrons, and as soon as you remove some electrons from the surface, it works kind of like a barrier for other electrons. So it means if you apply potential to such a layer, the electrons would, move from one side to another. However, on the way of contacts of different particles, there would be kind of like a barrier. Yeah. So as higher this depletion region or space charge region, so the region which contains, kind of positive charge, yeah, because there are electrons which are removed, you have higher barrier. Yeah. So, and as soon as you expose such surface, you add a bit of some reducing gas like hydrogen or CO or methanol. These molecules are interacting with this. You have simply chemical reaction, yeah, and then you decrease the number of atoms on the surface, and this actually decreases this space charge region, and it decreases the barrier for the electrons, other electrons which are inside to flow when for the current to flow through the layer. Yeah. And as soon as you have, for example, even more oxidizing environment, and this is the case if you have some nitrogen dioxide or nitrogen oxide, you would create even higher these space charge regions. And then it means that you even higher. So it is the way how, why the sensor is actually changes its resistivity when it is exposed to different gases. Yeah. And then, also what should be said that this explanation, this is kind of, accepted, but however, there are no much, experimental experiments which would confirm that it is true. Yeah. There are some other explanations. Sometimes people say that when you expose the surface to such reducing gases, you can create the oxygen vacancies on the surface, for example, and this results in the kind of appearance of additional electrons at the surface, because you remove one oxygen always leaves two electrons at the surface. So this could be also the reason why, I mean, the resistance of such layer is changing when it's exposed to some reducing gas. Yeah. So I mean, so it was the idea that we thought, okay, we might try to use the NAP XPS for such studies. We might try to detect if we can see maybe chemisorption oxygen on the surface. Also, we can try to explain if there is some chemical reaction, if there is a reduction of the surface. So you can see it using NAP, using XPS. Yeah. So we just fabricated very simple gas sensor. So with 2 electrodes, we contacted it. I mean, it was very, I mean, qualitative way for measuring resistance. I mean, only using two points. However, I mean, I will show that it was enough just for qualitative estimation if the sensor works. So then we deposited some tin oxide nanostructured layer on 2 electrodes, and we were measuring the resistance of this layer between these 2 electrodes. So here is some resistance measurements. We were exposing such sensor to, for example, oxygen mixture with ethanol. So ethanol was used as this reducing gas. Then again, oxygen, you see that it was kind of, I mean, working in a proper way. I mean, as N-type semiconductor. Also, it was interesting that when you, for example, expose such a sensor to just argon, then I mean, you also have a decrease of resistance, yeah, and pure ethanol, of course, and even UHV was decreasing. So it was done at 300 degrees C, and at each of these exposures, we were doing NAP XPS studies of the surface. It means, I mean, so we were following the thin, I mean, peaks, which I mean, are used to explain what is the chemical composition of the tin oxide. Yeah, it was found that I mean, doesn't matter to which actually mixture we were exposing. Tin was not changing much. Only I mean, at the beginning there is a change of its position, which is I mean, related to the change of the work function of the surface. So it means that when you have the absorption of a gas on the surface, so there is a chemisorption, you create some such things as a band bending. Yeah, so it means that your surface is partially, I mean, has the charge distribution, and then it means that the position of the peaks is changing. However, it is I mean, it is works for all peaks, so it is not just the proper of tin oxide. It is I mean, these shifts are happening always when you expose some surface to gas. So then you can calibrate this. So it means that you put it on the same energy, the same as it is in case of inert gas or in vacuum. And you can see that the tin oxide was just almost, I mean, the same. It was not changing at all. So we can say that there is no reduction of tin oxide when you expose it to ethanol, oxygen mixture, or to even pure ethanol. Also, I mean, yeah, also we, of course, detected other spectra, which is oxygen and carbon 1s. So we were trying to identify if we can see some chemisorption oxygen there, and I mean, it's decreasing when you expose to ethanol. However, it was very difficult because I mean, the layer was kind of a bit defective, and it contained some signals. So it was very difficult to say something with from oxygen. However, from carbon 1s, it was seen that if you have a mixture of ethanol and oxygen, you see that there is a formation of acetaldehyde, and it means that there is a reaction. I mean, so it means that then there was a simple oxidation of ethanol to I mean, through the acetaldehyde pathway. So actually, these experiments kind of I mean, confirm that the mechanism, which includes the interaction of the molecule with some chemisorption oxygen, it is the some kind of responsible for the change of resistance. Even so, we couldn't find any chemisorption oxygen on the surface. It is, I mean, its intensity is very low. And I mean, it was just somehow lost among the other, I mean, species. So yeah, okay, we can go to another I mean, type of experiments. So, for example, you can study not only, I mean, as I said, catalyst surfaces and its interaction with gas. You can try to, I mean, improve the experiment and try to measure some working devices. So to do kind of operando studies on some, I mean, electrochemical devices. And first example, this is solid oxide fuel cell. It can also work as an electrolyzer. So it means that it is the device which can chemically, I mean, can transform or can change the chemical energy or energy of chemical bonds directly to electrical power. Yeah. So you can, if you have, for example, hydrogen and oxygen, you can do two things. First, you can simply burn this hydrogen and use the heat which is released, and then use power station and somehow produce electricity. However, you can try to work in a different way. So you use, for example, solid oxide fuel cell, which contains two electrodes. On one electrode, you supply oxygen, and on another hydrogen. The oxygen dissociate on the one side to atomic oxygen, and it can be transported to the anode side by special electrolyte. And then here this oxygen interacts with hydrogen and forms water. Yeah, so you do chemical oxidation of hydrogen by producing electricity, because I mean, when you have two different reactions on two sides of such device, you have their formation of two different potentials. It comes from thermodynamic, yeah, from I mean, yeah, Gibbs energies and so on. And then of course it means that if there are different potentials, that the electrons which are formed here, I mean, they would always, I mean, flow through some external circuit if there is, if I mean, these two electrodes are connected. So you have simply device which I mean, work as a battery. So what is interesting that, I mean, you can have just standard like configuration when it is I mean, when hydrogen and oxygen is supplied on two different sides. However, you can build one chamber SOFs, it's called. So you can have two electrons on one support, and this support, it is actually this electrolyte. So depending which type of catalyst you have, two different reactions would happen here. So for example, and it can work also as an electrolyzer. So in this case, when you, I mean, leave it as it is, I mean, thanks to thermodynamics, I mean, the direction is like this way. So you have oxidation of hydrogen to water. However, if you would supply some power to such device, I mean, you would reverse the reaction. So it means that you can decompose water on two different parts, on oxygen and hydrogen, and send oxygen to this side. And here you have evolution of oxygen. So I mean, both are equivalent. So it means, I mean, you can use it, I mean, in two different ways. And in our case, I mean, when you build such a planar one-chamber SOFs, you can try to study the chemical, I mean, reaction on the surface of each electrode and on the surface of electrolyte, simply by approaching the nozzle to such electrodes and by applying different potentials. I mean, work in the electrolyzer, in the SOFs or fuel cell mode, and then try to answer, I mean, some questions, because usually all those electrodes and these electrolytes, they are quite complex materials, quite complex oxides, and it is quite important to understand what is, I mean, what is the function of each element inside this material when it works. So here is one example where people built such a planar fuel cell. They had their three electrodes. One is, I mean, this electrode for this yeah, this is, I guess, oxygen reduction reaction, if I'm sure. Yeah. So here it's cerium oxide, and then there was one electrode is just pure platinum. Yeah, this is the schematics of this construction, and you see that you can simply approach with the nozzle, and you can measure at different points from. There is also, of course, some counter electrode, which is simply collecting the electrons which are created in the catalytic layers. So you can simply scan such a device and measure at different points, and also do the chemical analysis. So you can, for example, detect what is the concentration of cerium 3+ and cerium 4+, I mean, atoms, and I mean, where is you can also feel the potential of the surface, because I mean, the electrons which are detected when you do it in this configuration, they always, I mean, feel the potential of the surface. So you would have the partial shift of the peaks. So you can, I mean, get some kind of information which is shown here. So here it's like, I mean, several points at which you can, I mean, at which this sample was measured. I mean, close to this cerium electrode, yeah. And you see that, for example, I mean, depending on the potential on such devices, you can have, I mean, different, I mean, reduction of the ceria. And you can, I mean, judge that if you have the reduction of cerium, it means that there is the place where the reaction takes place, yeah. Because here you have, in this case, it is shown as for electrolyzer, yeah. So it was a water decomposition, yeah, and formation of some hydrogen, yeah, molecules. And then, yeah, so here is some 2D map which shows you people were scanning, I mean, at different distances. So it is starting from some far place of the interface where this yttrium is interacting with ceria, and when the ceria is on this gold electrode. So you see that in this region, which is close here at some distance, you have no cerium 4+, so the reaction takes place exactly here. You can even try to, I mean, follow some dynamics, some diffusion, how far, I mean, this potential is filled by, I mean, what is the decrease of potential? Because as soon as potential is decreasing more, then I mean, at some point the reaction stops. So I mean, this is just example of what kind of, I mean, more sophisticated measurements you can do using XPS. Another way is to study another type of fuel cell. This is this PEM fuel cell, proton electrolyte membrane fuel cell, and in this case, the working principle is similar, maybe a bit different, because you again have two electrodes. On one electrode, you have dissociation of hydrogen, and this hydrogen is transported by the membrane to the cathode side. So in case of SOFs, which works at very high temperature, I forgot to say that usually you need higher than 500 degrees C, but usually, yeah, even higher. So you see that it's already red completely, the sample. In this case, you work at temperature which is not higher than 100 degrees C. And here, I mean, you have transportation of hydrogen to cathode side, and here you have, I mean, this is called hydrogen oxidation reaction when you oxidize hydrogen, yeah. And here you have the oxygen reduction reaction, yeah. No, oxygen oxidation reduction and hydrogen reduction reaction, yeah. I think it's like this. And then again, you can, I mean, it is also interesting when you have on both sides you have catalyst, and it is sometimes interesting if you have some kind of complex catalyst to understand what species are doing what, I mean, in these two reactions. So for this, I mean, people constructed such a device. So here you see that I mean, there is a fuel cell which I mean, on the cathode side you have some catalyst, for example, pure platinum. It is quite often used. So you can build such a cell inside the nacelle, and you just need to isolate the somehow one side from another. So one side can be hidden somewhere in the stage. I mean, and there you can supply hydrogen and, for example, water, because for conduction the membrane needs to be like wet. And then on the another side, I mean, this side can be just simply nacelle, which is filled with oxygen, for example, and you can try to analyze such a catalyst on the surface. I mean, by XPS, yeah. So you can follow the chemical state of the catalyst. I mean, when the fuel cell is in operational mode. So here is the kind of examples of spectra which you can obtain. You can expect, of course, that there will be some OH group, some oxygen absorbed, and so on. So you would, for example, it was measuring the oxygen spectra. Here are some references showing what different species where they have peaks, and this is what was measured on the surface of such cathode in presence of 0.4 torr of water. So it's kind of 0.5 millibars. And then you see that people were also trying to, applying different potential to such fuel cell. It means when you, load the fuel cell, you try to, take some current from anode side and send it to cathode side. Then it of course results in a different potential between these two electrodes. And depending on the potential between them, you can see how different species are changing. For example, you see that when there is a very low potential, you have mainly water on the surface, because this water, is coming from the membrane. As soon as you increase, the flowing current, you increase the potential, then, you have the change of, there is formation of some OH group and oxygen. What I said, you always feel a bit the potential, so you should also count for it, because in such case, these electrons which are leaving the surface, they would always feel the potential which is applied to the electron. So it means that your peaks are shifted by this potential. So here is some dependence of the potential of the peak. The feeling, what electrons are feeling, how it depends on what is applied to this surface, yeah. And then you can, having such measurements, you can try to explain what happens on the surface at different potentials. When just pure water adsorbs, when you have dissociation to OH groups, and then there is a formation of some complexes which are OH with oxygen, yeah, and so on. So everything this comes from the spectra. You can also try to analyze you can fit this spectra more precisely, to try to detect what species you have there. Of course, this is quite a complicated spectrum, because people, they fitted it with many peaks, which are, related to different species. Also, of course, sometimes you need some calculation. So this is some DFT and Monte Carlo simulation, which helps you to explain your experimental data. And finally, actually, you can, explain what is going on the surface. So, yeah, I think the last example which I want to show you, this is what I said is the study of some a solid electrolyte interface. It is not the interaction of solid with gas, but with liquid. And as I said, it is usually done when people try to study some electrochemistry. So they have some working electrode, they pull it to electrolyte, then they dip it to electrolyte, and then pull it a bit up, and then by applying potential to this electrode, the potential is still filled through this thin layer which is on the electrode, and you can analyze it. You can do there some cyclic voltammetry, and then you can follow the structure. For example, it was just simple experiment which shows that this principle works with platinum. So it was shown how the intensity is changing, because there is a liquid, of course. So this is the without liquid, it is with liquid. And then when you apply some potentials, you can see the formation of some oxygen species. So you can answer the question at which potential is usually platinum is oxidizing. And this is quite important in case of study of different fuel cells and so on. So it is usually like after like 1.2 volts, you have formation of some oxide on the surface, and you see that you can somehow see it even directly using an XPS. Yeah. So okay, so I guess I would finish with this. So just to conclude, I can tell that XPS is can be quite useful tool for investigation of chemical processes on the surface of solid material. It can be measured in presence of gas or in presence of liquid sometimes. And I mean, of course, as I said, it is better to use soft X-rays for if you want to really see good signal from your adsorbed species on the surface. However, it brings another problems with intensity, and usually it cannot be done at higher, I mean, pressures. So if you do some measurements at synchrotrons, they're usually below 1 millibar. I mean, it's some tens of millibars. I mean, however, you can also use XPS with conventional X-ray source, and I mean, can also get some signals, but usually, I mean, you need a long time for scanning these spectra. They are very noisy, I mean, which are responsible for the adsorbed species. Yeah, and then, I mean, you can also adapt the NAP-XPS for studying, I mean, some more sophisticating, for performing some more sophisticated studies. It's like study of gas sensing mechanism, some cells like fuel cells and other things. So I would like to thank you for listening.